Good day, I'm Christian Celajes of BCH31, and I will be reporting a journal entitled Stop Economic Synthesis of Melosatin A by Bolivar et al., published in American Chemical Society. This journal will be presented starting with its abstract, then introduction, problem, literary review, objectives, retrosynthesis, synthetic steps and mechanism, and lastly, the conclusion. According to the abstract of the said journal, this contains an efficient and straightforward route toward the synthesis of an isatin type natural product. The study utilizes a dry substituted aniline as a key intermediate in synthesizing melosatin A, which only used 5 steps with an overall yield of 41%. Also, in its final step, it uses a Martinet isatin synthesis. Before the synthesis and mechanism, let's introduce the concept first. We aim to synthesize the natural product melosatin A, which is a derivative of isatin or 1H-indole 2,3-dione. It has a privileged structural motif, meaning its molecular framework can provide ligands for multiple receptors through structural modification, thus a biologically active molecule. Therefore, it has a valuable synthetic intermediates in the areas of heterocyclic and pharmaceutical chemistry. Its biological activities include cytotoxic, antimicrobial, and enzyme inhibition. Isotins are synthesized from the roots of the Colobian shrub. Other than isotins, there are quinolones, pyridines, and cyclopeptides. From the isatin family, there is this structure, which is called melosatin A. Its structure has oxygen functionalities at carbon 5 and carbon 7, and a phenylpentyl motif at carbon 4. This is used for anti-cancer, antimicrobial, and anti-inflammatory medications, and has advantages such as higher potency, specificity, and stability. But what are the problems with the synthesis of melosatin A that needs to be resolved? First, the former total synthesis of melosatin A includes 7 steps, has a very low overall yield, and a not reported last step, the Stoller reaction. Second, only the Colombian shrub is the source of this reduced and quite rare group of 3-keto-indolinones. However, according to the other literature, isotins can also be isolated from the floral parts of Guianan evergreen tree, the Japanese orchid, fungi, parted glands of toads of genus Bufo, and submarine mollusks. Adding to its uses, other isatin derivatives can be used as selective inhibitor of the enzyme MAOB, hypertension treatment due to induced dopaminergic or D2 antagonist activity, and inhibitor of enzyme CDK2. To make it more significant, melosatin A shares a structural similarity with the substitution pattern of the carbocyclic ring of melovenone, a plausible biogenetic origin. To solve the melosatin A synthesis problem, it was necessary to design and execute a synthetic route that minimizes the number of steps required, while maintaining high yield, efficiency, and scalability for an efficient production, improved scalability, waste reduction, and enabling derivative synthesis and scientific advancement. Since we're here, now let's go for retrosynthetic analysis that will help the analysis and plan the synthesis of melosatin A. Since this is in reverse, we will start with melosatin A. The retrosynthetic disconnection of the bonds nitrogen and carbon 2 and carbon 3 and carbon 3A unmask the polysubstituted aniline and an oxalyl derivative as logical precursors. It was conjectured that this is isatin synthesis involving a 2 carbon atoms like the oxalyl chloride, which is called the Stolle reaction. Continuing the analysis, the dissection of carbon 2' and carbon 3' bond unveiled two fragments, the phenyl 1 butene pendant side chain and the allyl benzenoid, resulting from functional group conversion on the nitrogen atom. It can be said that doing a olefin cross metathesis from these two can provide the aniline intermediate. Now, further carbon oxygen and carbon nitrogen bondness connections uncovered an economic and readily available product. This is called eugenol, with, with an IUPAC name 4-allyl 2-methoxyphenol. It is a monoterpenoid compound with a phenolic hydroxyl and carbon-carbon double bond. It is synthesized from clove, often used as a spice, but now eugenol is synthetically synthesized using methyl catechol and chloryl aniline. The retrosynthetic analysis of Melosatin A leads us to eugenol, which will be the starting product of the new total synthesis of Melosatin A. Here is the overview of the synthesis of our target product. The experiment was done in, in dry argon atmosphere and in oven-dried glasswares. The synthesis commenced with the regioselective orthonitration of eugenol. This was performed by heating a mixture of the commercial product with a solid ammonium nitrate and potassium bisulfate in acetonitrile at 80 degrees for 24 hours. The reaction between ammonium nitrate and potassium bisulfate produces a nitronium ion and water. The water obstructs the hydrogen, leading to formation of carbon ion, which then acts as a nucleophile that will attack the positively charged nitrogen of the nitronium ion. This efficiently provided a 96% yield of 4-allyl 2-methoxy-6 nitrophenol after filtration of the reaction mixture through a short pad of silica gel. In line with previous reports, longer reaction times strongly affected the reaction outcome, diminishing yields and giving rise to highly impure samples, which could be caused by the polynitration and product polymerization. Next, the projected Williamson-O methylation, also called Williamson ether synthesis, reaction of nitrophenol was accomplished with iodomethane in a refluxing absolute ethyl alcohol, using potassium carbonate as the base. Williamson-O methylation is a SN2 reaction, where an alkoxide ion, a result from the abstraction of hydrogen from nitrophenol by the base, acts as a nucleophile that displaces a halide ion from an alkyl halide to give an ether. This gives 5-allyl 1,2-dimethoxy 3-nitrobenzyled in 98% yield after 24 hours. With the required compound in hand, the olefin cross metathesis step was undertaken. This is a powerful synthetic tool that enables the facile preparation of hardly accessible compounds. In this step, our olefin nitrobenzene is reacted with 4-enyl-1-butene and refluxing anhydrous dichloromethyl under Grab's 1 catalyst. This was already discussed before, but let's remember the mechanism. Olefin cross metathesis is a swapping of the terminal carbons of alkenes using a Grab's catalyst, depicted here as Ru. This reaction works best when one of the alkene is present in excess, and that excess alkene is the 4-phenyl-1-butene. The first step is a cycloaddition between the alkene and ruthenium carbene to form a four-membered ring shown in step 1, arrows A and B. After this, the second is a reverse cycloaddition shown in step 2, arrows C and D, to give a new ruthenium carbene and a new alkene. The carbene can then be combined with the new equivalent of alkene in step 3, shown in arrows E and F, followed by another reverse cycloaddition in step 4. The geometry of the alkene is not very well controlled in this intermolecular reaction, so a mixture of E and Z alkenes are the product. From the cross-metathesis of our nitrobenzene intermediate in the excess alkene for phenyl 1-butene resulted to a 1,2-dimethoxy 3-nitro 5-phenyl-pen-2 and 1-yle benzene, which is consistently obtained in 73% yield as a mixture of E and Z olefins. The following step should produce this desired key intermediate. The seemingly easy concomitant NO2 group reduction and olefin hydrogenation proved to be hard to perform. After multiple trials, a promising solution was established. In this reaction, molecular hydride is generated in situ from triethylsilane in methyl alcohol in the presence of chloroform and 10% palladium hydroxide in carbon as a catalyst, which is a heterogeneous catalyst since it is not dissolved in the solution. Instead, the reaction occurs on the surface of the metal. Palladium is an electron-rich late metal that reacts with hydride to form metal-bound hydrides, which are more reactive toward alkenes or nitro group. Furthermore, late metals readily absorb alkene and other molecules with pi bonds onto their surface. The resulting hydrogenation products, lacking a pi bond, are not as bound as strongly to the metal and typically dissociate after hydrogenation, freeing up a site on the palladium for further reaction. Since the reaction takes place on the metal surface, high surface area is important for the reaction rates. That is why the metal is finely divided and absorbed onto a solid support such as activated carbon. Hydrogenation of nitro group to amino occurs in syn addition. Same with the olefin hydrogenation, where the carbon hydrogen bonds form on the same face of the alkenes. Since these new bonds are formed at the expense of carbon-carbon bonds, hydrogenation reactions of alkenes and nitro group result in the lowering of the oxidation state of carbon. That is why this is often described as reduction. Under these conditions, the desired aniline was obtained in 88% yield. Having a satisfactory route toward aniline, the Stoller reaction was tested. This involved the sequential addition of the aniline over oxalyl chloride at room temperature in order to maximize the formation of oxalamidoacyl chloride intermediate, followed by a cyclization reaction under solventless conditions. However, this resulted in extensive decomposition of the starting material, except for the related bis-oxalamide obtained in 43% yield, and a melosatin A of a disappointingly 3% yield. Aiming to circumvent this obstacle, Bolivar et al. Uses the Martinet isatin synthesis due to its mild and essentially neutral conditions, which employs diethyl ketomalonate as the 2-carbon synthon that would fulfill the synthetic requirements. This type of synthesis is a method of producing isatin by reacting an amino aromatic compound with an oxalomalonate ester in the presence of an acid. This is a century-old reaction which has been used sporadically in the past. However, in recent times, it experienced a revival, finding frequent use in the synthesis of natural product. However, one of the major drawbacks of this approach is the poor predictability of its performance. The Martinet isatin synthesis has a synthetic requirement, like what I said, the diethyl 2-ketomalonate. This was prepared by stirring a mixture of diethyl malonate and ceruc ammonium nitrate and acetonitrile under pure oxygen for 4 days at room temperature. Complete consumption of the starting material was observed, resulting in 67% yield of the target product. The Martinet reaction, which entails a series of successive operations, was now tested. The aniline was firstly condensed with the ethyl to ketomalonate in glacial acetic acid at 120 degrees Celsius, and after stirring for 4 hours, the reaction solvent was removed under reduced pressure, and the oily residue was treated with a base, 1 molar potassium hydroxide. Immediately, air was bubbled overnight, followed by an adjustment of the acidity of the medium to pH 2 to 3 by the cautious addition of 6 molar hydrochloric acid. This provided the expected isotin, Melosatin A, and 41% overall yield. Although the complete details of the mechanism of the Martinet reaction remains unknown, a mechanistic picture can be drawn. It can be conjectured that the reaction could proceed through an initial nucleophilic attack of the aniline to one of the ester moieties of an alkyl to ketomalonate in acetic acid to provide the amide. In turn, this intermediate could cyclize under the promotion of the electron pair on the nitrogen atom to afford species resulting from an isomerization or a 1,3 hydrogen shift that regenerates the aromatic ring. Subsequent treatment with aqueous 1 molar potassium hydroxide would cause hydrolysis of the ester and triggers the decarboxylation of the 1,3-dicarbonyl intermediate to deliver the 3-hydroxy-indolinone. Final oxidation of the latter by air bubbling would provide the related isotin after acidification with aqueous 6 molar hydrochloric acid. In conclusion, it is possible for an alternative reliable and efficient total synthesis of Melosatin A from Eugenol with only 5 steps lesser than the 7-step synthesis before, and has bigger yield of 41% overall yield. The reactions used each steps are orthonitration, Williamson O methylation, olefin cross metathesis, hydrogenation, and the Martinet isotin synthesis, requiring only 3 starting materials: the eugenol, the ethyl malonate, and the formatted phenyl 1-butene, which are all readily and commercially available. Now, thank you for listening. Here are my references, and we can now proceed with the question and answer for portion. First question: in the reduced selective nitration of eugenol, can we use H2SO4 or sulfuric acid instead of potassium bisulfate? Would it lead to a different result? The answer is yes. We can use sulfuric acid rather than the potassium bisulfate. However, the sulfuric acid in any form is notorious, and its safe disposal is one of the problems and concerns of chemical industries, and therefore its replacement with safer reagent is desirable. And the use of a safer and green reagent, the potassium bisulfate, resulted in more efficient, selective, and high-yielding nitration, with a more reasonable mechanism for generation of nitronium ion. To answer the second question, the use of sulfuric acid will lead to a lower yield, which is not desirable. Second question: further explain Stolly reaction and its mechanism. What was the reason why it resulted to a bigger yield of a different product instead of the target Melosatin A? Stolly reaction is a two-step synthesis for isotins. First step is acylation. The N-substituted aniline are acylated with oxalic chloride. then an intramolecular electrophilic substitution occur in the presence of a Lewis acid. It can be suggested that most of the common methods for the production of isotins become less than adequate when the number and lipophilicity of substituents on the targeted isotin are increased. Therefore, it was conjectured that the failure of aniline to afford melosatin A in satisfactory yields was a consequence of the nature of the substituents and steric effect re- present in the aniline derivative resulting from polyfunctionalization of the starting material. That's all, and thank you.